Yeah, so welcome to the third session of the Isogeny Club. Today we have the brilliant Maria giving an awesome talk on the problem of attacking the general isogeny problem. If you want to ask questions, then please just go ahead and do that. As I just said, the talk is being recorded, so just letting you know that, but we of course strongly encourage asking questions anyway. And also, if you after the talk remember some or come up with some question which you didn't come up with during the talk, then you can also ask on the ask crypto thread related to this talk, which Cran just posted in the chat. Well, take it away, Maria.
Awesome. Thanks for the introduction and for having me at the Isogeny Club. As Jonathan said, feel free to ask me any questions throughout. I don't have the chat up, but someone can just point to it if someone does ask a question. I'll be talking about attacking the general isogeny problem. And this is based on two works joint with Craig, Sam, and Jia. And so we'll be talking about the isogeny problem in both dimension 1 and 2. And I wanted to make this kind of a more relaxed talk, maybe giving more intuition as to how these attacks came about and the general idea behind them, and then talking more specifically about each attack in the two dimensions. Okay. So I'll first introduce the isogeny problem in dimension 1 and 2, then talk about how you can view this as a path-finding problem in some related graph, strategies for finding paths in a graph, and then its application to dimensions 1 and 2, and then some results that come from the papers with those co-authors. In isogeny cryptography, as maybe most of you know, we consider supersingular elliptic curves over finite fields where our prime is going to be of cryptographic size, and so it will be bigger than 3. And we're interested in elliptic curves up to FP bar isomorphism. So in particular, we can label each of these isomorphism classes by J invariants. And because our prime is bigger than 3, we can put our elliptic curves in this nice form, y² equals x cubed plus ax plus b. And then your J invariant is given by this rational expression. The denominator is never 0 because our elliptic curves are always non-singular. And so this expression is always well defined. And then importantly, for cryptography, every supersingular elliptic curve admits a model over fp². And all that means is that you can always write your elliptic curve in some form where your coefficients are defined over fp². And then this means that your J invariant will always lie in fp². And this is really useful because it means that we're never going to have to go to extension fields when we do our computations. And then we consider n isogenies between these elliptic curves. And these are just isogenies with kernel z mod nz generated by some point on your elliptic curve. And in cryptography, we normally force our point to be defined over fp² so that isogenies can also be done over fp². Okay. So then in its most general form, the isogeny problem asks you to find an isogeny between two supersingular elliptic curves defined over fp². And note very importantly that we're not assuming any torsion point information or that we know the degree of the isogeny. The first point is important because with this torsion point information, the problem is actually solvable in polynomial time. And I guess you can watch the first week of the Isogeny Club if you want to know more about that. And then, yeah, we also don't assume that we know the degree of the isogeny. Okay, so now moving on to dimension 2. So we want to generalize supersingular elliptic curves to higher dimensions. And so elliptic curves in 2 dimensions are just abelian surfaces. And yeah, there's this technical condition where we have to consider principally polarized abelian surfaces. And this is just so that we can sort of write down equations for these surfaces. And it's the right generalization of an elliptic curve. The reason why this never comes up in the dimension 1 case is because all elliptic curves are principally polarized. And so you can sort of just omit that like technical term. But yeah, you can, for the purposes of the talk, you can kind of ignore that, but it's just, you need your abelian surfaces to be principally polarized. And then the supersingular aspect is generalized in 2 dimensions to superspecial. And I think this is kind of a confusing point that it has 2 different names. But this is because supersingularity in 1 dimension has many different equivalent definitions. So you can have that the trace of Frobenius vanishes mod p, but you can also have some condition on, you know, what the p torsion looks like. And these are all equivalent, and you call this condition supersingularity. But in dimension 2 and above, these become distinct. And in fact, the correct property that you want to generalize corresponds to superspeciality, which is the fact that your trace of Frobenius vanishes mod p. And yeah, so it's kind of unfortunate that we don't call supersingular elliptic curves superspecial abelian curves, because that's really what it should be called. But yeah, superspecial abelian surfaces are just sort of the analogues of these objects in dimension 2. So there are 2 types of abelian surfaces. The first is sort of this decomposed type, where it's just a product of elliptic curves. And if your surface is superspecial, then the elliptic curves will be supersingular. And then the second type is a Jacobian of a genus 2 curve. So in genus 1, for example, if you have a genus 1 curve, then this elliptic curve is also the group, but this isn't true in 2 dimensions. And the Jacobian is sort of your group attached to the curve. And the Jacobian is what you need to add points and do all those cool operations. So we consider the Jacobians of your curve, and these are the abelian surfaces. Like in dimension 1, we consider them up to FP bar isomorphism, and we label these isomorphism classes with, in the first case, sets of J invariants. So just the J invariant of your first elliptic curve and the J invariant of the second elliptic curve. And because order doesn't matter, you consider the set of these. And then in the second case, we consider these Igusa-Clebsch invariants. And these are just sort of rational functions in the coefficient of your curve. And these actually lie in some projective space that's weighted. And so the subscript here just denotes the weight of the like corresponding coordinate in your projective space. Okay. And like in the dimension 1 case, every superspecial abelian surface admits a model over ft squared. And this is actually one of the reasons why superspecial is the correct generalization, because you have this nice property where you can get a model over fp squared. And also, in particular, your invariants will all lie in fp squared. I guess that's obvious in the first case because your elliptic curves are supersingular, the less obvious why these should all lie in fp squared. But yeah, if you're superspecial, then this is true. Yeah, and then how do we generalize n isogenies? Well, we now consider n isogenies, which are just isogenies. Okay, there is a typo there, but it should just be an n isogeny is an isogeny between abelian surfaces, where your kernel is just two copies of z mod nz, and it satisfies this maximal isotropic condition, which means that if you take 2 points in your kernel and take their n veil pairing, then it's 1. And all this condition is ensuring is that your image curve comes with a polarization, a principal polarization. And in genus 1, we don't have to worry about this because this will always be satisfied. But when you go up to higher dimensions, you need this extra condition, which just means that the isogeny sort of behaves well with the polarizations of your surfaces. Okay, and then you can count the number of NN isogenies for a surface from a surface A. This will be important for like the number of outgoing edges in the corresponding graph. And it's given by this formula here. In particular, when n is prime, it should be n squared plus 1 times n plus 1. So it's sort of like order of n cubed outgoing isogenies. And then the superspecial isogeny problem asks, in 2 dimensions, asks to find an isogeny between 2 superspecial abelian surfaces defined over fp squared. And again, we don't assume any extra information. Just as sort of a note, I'll probably not say principally polarized from now on because it's a bit of a mouthful, but just assume that everything is. Okay, so the isogeny problem in both dimensions can actually be viewed as a pathfinding problem in the related graph. So what are these related graphs? Well, in dimension 1, we consider n isogeny graphs, which I'll denote by this capital gamma sub 1. And here the vertices are fp bar isomorphism classes of supersingular elliptic curves. And as I mentioned in the first slide, you can represent these by J invariants. And then in an n isogeny graph, your edges will be n isogenies. So some properties, there are around p over 12 vertices. So in particular, the vertex set is finite. A random walk of log p steps, so comparatively short with respect to the number of vertices, is almost as good as uniformly sampling your vertices. So all this means is that the graph mixes really well, and in fact, it has optimal expansion properties. And so we call such a graph Ramanujan. And pathfinding is conjectured to be hard for classical and quantum computers. So I guess that's why it's interesting for cryptography, because this problem of finding paths in the graph is conjectured to be hard. So then if you find a path between 2 nodes, say J1 and J2, then this is the same as finding an isogeny between the corresponding elliptic curves. And just as sort of a note, we normally keep the vertex set of our graph the same, but we might change between different edge sets, which means we might walk in the 2 isogeny graph and then change to the 3 isogeny graph. but our vertex set will always be the same. So this isogeny doesn't necessarily need to just be like a power of 2. If you walk in the 2 isogeny graph, you might switch between the different edges. Yeah. Okay, and in 2 dimensions, we have a very similar graph where now your vertices are just your abelian surfaces and your edges are NN isogenies. And I'll denote the graph by now a gamma sub 2. And similarly, there are finitely many vertices. Again, this is one of the reasons why superspecial is the correct generalization, because you have a finite vertex set. There are around order of p cubed vertices. And you may ask, is this graph also Ramanujan? Well, in a paper by Floret and Smith, they actually give counterexamples for small primes where it's not actually Ramanujan, but they show experimentally that the expansion properties are still good enough for cryptography. But the hardness of pathfinding in this graph is still a bit unknown because there isn't a lot of sort of theorems proved about this graph. For example, I think it was only 2 years ago that Jordan and Zeitman even proved it was connected. So there's still a lot to be learned about this graph, in particular, what are its expansion properties. Okay. And then similarly, finding a path between the nodes is the same as finding an isogeny between them. Okay. So how do we find paths in this graph? Well, I guess a first attempt would be to walk in the graph from the start node until you reach the end node. And as the graphs are finite, this will terminate, but it's probably not going to be very efficient because our vertex sets are very big, like of size p or p cubed. And so this won't really be efficient. And so we can ask, can we find a better method, excluding, so I won't be talking about a meet in the middle approach in this talk. So excluding that approach, is there sort of a better method which we can use? So the first thing we can try is to maybe reduce it to an easier problem. So you've got a graph and you're trying to find paths in the graph. Is there a way that you can reduce it to an easier problem? And it turns out that our graphs will have these special nodes where path finding is easier. So we'll have the white nodes in the graph, which are just your sort of generic node. And then you'll have this subset of nodes, which forms a subgraph, which will be special. And they're special because path finding will be easier in this subgraph. But the problem is they will be rare. So this subgraph of special nodes will be rare. So then our finding paths between the start and end nodes will be split up into 2 steps. So the first will be to find paths from your start and end node to the special nodes. So you just walk in the graph until you find a blue node, and then you go from your end node and you walk around until you find a blue node. And then once you found your blue nodes, you can walk in that subgraph and find a path a lot quicker. Okay. And then you can, so this step in the subgraph should be easier. And so your first step is sort of the bottleneck, the bit in red. And then you can concatenate the paths to get the full path. Something that I forgot to mention before is that our graphs are undirected. And so you can actually sort of reverse the arrows here and compose the path in like one direction. And this is because in our isogeny graphs, we have the dual of the isogeny, which gives you the other direction. And this is the same in dimension 2. You also have a dual, which will give you the other direction. Okay. So as the first step is the bottleneck, we focus on improving this part of the algorithm. And so we want to walk in the graph until we reach the blue nodes. So that's kind of a little bit of a problem, I guess, is that at each step of the walk, we only reveal one node. So this isn't really, revealing a lot of nodes in the graph. So you can ask, can we detect more nodes at each step? So is there a way that at each step, we can do some sort of like special detection to reveal more nodes? And if you reveal more nodes, then you could hope to find a blue node more quickly. So how would this work? Well, your first step is to choose a set which you will perform this like detection for. And then you're like at the current node, the orange node, and you perform your detection for these elements. So say detecting for D1 reveals 3 nodes, then you reveal 4 nodes, and then so on, and you reveal these nodes and you stop performing your detection. Then you've revealed all of these gray nodes in the graph. And this is a lot more than if you had just taken a step and revealed one node, right? And then if you don't detect a blue node, then you can just move on to another node by taking a walk in your graph and then doing the detection again. So the idea is that you've sort of revealed a larger proportion of these white nodes at each step. So yeah, so how can you choose such a detection step? Well, suppose you can perform this efficient detection for some elements in a set S, and you want to choose this detection set. Well, performing detection for these elements in the set will, of course, increase the cost of, taking a step in the graph. If you were just to walk in your graph and take steps, then this would definitely cost less than taking a step and performing some detection. But the key point is that you're revealing more nodes. And so what you actually want to do is choose a set, D, that minimizes the cost per node revealed. So here your nodes revealed are both the nodes that you've walked on and the nodes that you've detected using your cool detection. And so if this cost at the top is small enough compared to the nodes revealed, then you can hope to reach the blue subgraph in a much quicker amount of time and hope to improve the concrete complexity of your attack. Yeah. So now so this is sort of the general framework of how these attacks work and how we will improve on the attacks. So now I'll discuss their applications in dimension 1 and dimension 2. So in dimension 1, this is based on the Supersolver paper with Craig and Jia Shi. And yeah, so now I'll talk about how you can apply these ideas to solve the general isogeny problem in dimension 1. And recall that you can reframe this problem as a path-finding graph in your supersingular isogeny graph. So we want to find a path between 2 nodes J1 and J2. So first, how can we take steps in this graph? So to walk around in the graph, we need to know how to take steps. So in the n-isogeny graph, we're actually going to use modular polynomials. So the modular polynomial of level n parameterizes pairs of n isogenous elliptic curves. So what does this mean? Well, firstly, they're symmetric of degree dn, which is given by this formula here. And in particular, dn is equal to n plus 1. So this will mean that the number of outgoing isogenies from each node is sort of order n in the dimension 1 case. And then the key property of these modular polynomials is that if you evaluate them at a pair of J invariants, and this modular polynomial evaluates to 0, then these two J invariants actually correspond to the J invariants of elliptic curves, which are n isogenious. And so you can use this to walk in the n isogeny graph by firstly evaluating your modular polynomial at J, say the current node that you're on J, and this will give you a polynomial in X. And then you can take the roots of this polynomial, and these will be the neighbors of your node J in the n isogeny graph. So more pictorially, maybe, to make it clearer. So what we do is we actually want to take non-backtracking walks. So we don't want to come back to where we came from. So we store both the current J invariant that we're on and the previous J invariant. We evaluate our modular polynomial at the current J invariant and then quotient it out by the X minus the previous J invariant. And this quotienting out just makes sure that you don't backtrack. So you kind of remove that root from your polynomial. And then this modular polynomial will have dn minus 1 roots. So you can compute these roots and choose one of them to walk onto, and then sort of repeat this process. So we choose to take these walks in the 2 isogeny graph because this means that dn minus 1 is just 2. And so actually all we have to do is factor a quadratic polynomial. And this is a lot cheaper than if you walk in the 3 or 4 isogeny graph, where you'll have to be factoring a cubic or a quartic, etc. And actually, in this case, because we're factoring a quadratic, if you find one root of the quadratic, you get the other one for free. So you actually reveal 2 nodes in your graph at each step, which is a nice bonus. Okay, so what's the special subset in this case? Well, it turns out that this special subset where your path finding is easier is the subset of J invariants lying in FP. So you have your isogeny graph, and most of your J invariants will lie in FP squared. In fact, order of P of them will. And then order of the square root of P of these nodes will lie in FP. And this FP subgraph is a lot more structured. And so it's comparatively easier to find paths in this subgraph. But as I mentioned before, they're quite rare. So these blue nodes are quite rare in the graph. So Dels and Galbraith use this to give the best attack against the general isogeny problem. And so given a start and an end node, the first step is to walk to your special subset. And because of the proportion of the nodes in the graph, you expect this to terminate in sort of O till of the square root of P time. And then once you found these steps, you can find a path between the 2 blue nodes. And this can be done in the 4th root of P time. And this is what I meant by easy, like easy to find paths in the subgraph, It doesn't necessarily mean that it's like polynomial time, but the bottleneck is this first step, because the sort of the asymptotic cost is dominated by finding this subgraph. And then the desired map between the two nodes is just the concatenation of the paths, where you take the dual of the last path to get it in the reverse direction. And that's what this hat sort of signifies. It's just taking the dual of the isogeny. Okay, so to improve the detection, we want to sort of perform this detection for n bigger than 2. Like we don't just want to walk in the 2 isogeny graph. We want to see if we can detect FP neighbors in the n isogeny graph where n is bigger than 2. So the question we want to ask is, does your modular polynomial of level n, when it's evaluated at the node that we're on, does this have a root in FP? And we want to answer this question for n bigger than 2. So sort of the key observation is that at each step, we don't actually have to compute these roots. In fact, computing these roots is really expensive for n bigger than 2. And so we want to do this in a way where all we do is detect whether it has a root in FP without actually knowing what the root is. And then if we detect that it does have a root in FP, as a post computation, you can compute the actual value of this root. So what we do is we evaluate this modular polynomial at JC, and then just let F be this evaluation. Then we compute the greatest common divisor of F and the Frobenius map applied to F. But by this, I just mean that you're applying the Frobenius map to each coefficient of F. And then if the degree of this divisor is 1, then F has a root in FP. And if the degree is 0, then F does not have a root in FP. So this is how we detect or how we answer this question. And you may be wondering what happens if the degree is bigger than 1. Well, in fact, for our application, this is sort of happens with negligible probability. And so we sort of discard those cases and just take another step in the graph. And because it happens sort of negligibly often, it doesn't affect sort of the efficiency of our attack or the effectiveness of it. And also in our paper, we show how we can transform F and pi applied to F, which now lie in FP squared, whose coefficients now lie in FP squared, because we've applied, because we've evaluated at JC. And we show how we can transform these to give polynomials whose coefficients are now defined over FP. And in fact, this transformation doesn't involve any FP squared multiplications. And so, yeah, because these polynomials have the same GCD as F and pi of F, then we actually avoid all of the multiplications in FP squared. And we can perform this detection using just multiplications in FP, which makes it even more efficient. Okay. So how do we choose the detection set? Well, we have modular polynomials for all sort of integers up to, well, you can in theory compute them for like as big as n as you want, but Sutherland actually has a a large list of them on his website that he's computed. And so in theory, we can do this detection for the modular polynomials on his website. And we want to choose a subset of this to minimize this cost. So the cost of taking a step in the graph plus the cost of detection, and then over the nodes revealed by walking in the graph and by detecting them. And in our case, this corresponds to the cost of computing the square root of this, this modular polynomial evaluated at JC and quotiented out by this factor. And we reveal 2 nodes at each step. So that's why there's a 2 here on the bottom. Okay. So now moving on to dimension 2. So this is based on joint work with Craig and Sam, and there will be an ePrint soon. And we consider the general isogeny problem in dimension 2, which, recall that you can view this as finding a path in the superspecial isogeny graph. So again, we need to talk about how we can take steps in this graph. So taking a step is just in your NN isogeny graph is just computing one of the NN isogenies from the node that you're on. And so we choose n equals 2 to be able to exploit fast Richelieu isogenies. And Richelieu isogenies is just another name for 2-2 isogenies, named after a mathematician who studied them a lot. And also, the expansion properties of random walks are actually most well understood for this 2-2 isogeny graph. As I mentioned previously, these isogeny graphs are less known, but the most sort of empirical evidence that we have for them is actually on the 2-2 isogeny graph. And so when we take random walks in the 2-2 isogeny graph, we have better confidence that we are actually taking random walks. And that we are getting like good expansion from these walks. So for each node, there are 15 outgoing 2-2 isogenies, but we actually restrict to these good extensions, and there are only 8 of these. So we have 8 possible nodes that we walk to. And these good extensions just ensure that there are no trivial cycles, so you don't get sort of stuck in the loop. So in a picture, what is a good extension? Well, if you have 3 nodes here where you've walked from A1 to A2 and from A2 to A3, these isogenies, because they're 2-2 isogenies, will have the following kernels, which is just 2 copies of Z mod 2Z. And you can sort of consider the intersection of the kernel of this isogeny with the kernel of the dual isogeny of phi1, which goes from A2 to A1. So if the intersection is just the whole thing, so if they're the same, then it turns out that phi2 is actually the dual of phi1, right? Because the kernels are the same. And so you're just backtracking onto the same node that you've come from. But in genus 2, because we have 2 copies of Z mod 2Z, you can actually have the case where the kernels aren't the same, but they intersect non-trivially. So in this case, when they intersect at Z mod 2Z, then this corresponds to a bad extension. And this kind of means that you've come back to where you've come from just a little bit, like sort of halfway back to where you've come from. And if you take enough of these, this corresponds to a trivial cycle in your graph. And because these don't really give you very good expansion, we restrict to the case where this is a good extension of phi1, where these kernels intersect trivially. So what is our special subset in the dimension 2 case? Well, every abelian surface is isomorphic to either a Jacobian of a curve of genus 2 or to a product of two elliptic curves. So your vertex set of your NN isogeny graph is equal to the union of this JP set, which is just your abelian surfaces that are isomorphic to a Jacobian, and this EP set, which are your abelian surfaces isomorphic to a product of elliptic curves. And so your special set is actually this EP set, which is sort of when your abelian surface is decomposable in a way. So you have order of p cubed nodes where your abelian surface lies in JP. And this is the majority of the nodes in the graph. And then you have this special subset of nodes, which are rare, where your abelian surface is an EP. And there are around order of p squared of these. And walking in the, finding paths in between the blue nodes is a lot easier because you can reduce it to just finding paths between the elliptic curves. And so you reduce it to the dimension 1 case, which should be easier than the dimension 2 case. So this is actually the idea behind the attack by Costello-Smith. So you have a start and an end node. Your first step is just to find paths until you hit a blue node, which is just a product of elliptic curves. And again, because of the proportions of the nodes in the graph, you expect to do this in order of p time. And then you find a path between the two blue nodes. And as I alluded to before, what you do is you find an isogeny between the two first elliptic curves using, for example, the Delft-Galbraith algorithm. Then you find an isogeny between the second elliptic curves in the product. And then you can sort of patch these up together and create this isogeny pi, which takes one of the products to the other product. And then because you can do this using Delft-Galbraith, this terminates in sort of order of the square root of p time. And then your desired map is just the concatenation of these paths, where again, you take the dual of the last path. Okay, so again, here the bottleneck is the first step, which is walking in your 2-2 isogeny graph until you find a surface which is 2-2 split. And what do I mean by this? Is just a Jacobian of a genus 2 curve is said to be NN split if there exists an NN isogeny taking your Jacobian to a product of elliptic curves. So what we're doing in the first step is we're just walking around until we find an abelian surface that has a 2-2 isogeny to a product of elliptic curves. And this just means, or another way to say this is that it's 2-2 split. So in more detail, we start on a node, say A0, which is lies in JP. We take a Richelieu isogeny, which is just a step in our 2-2 graph to A1. Then from our Richelieu isogeny formulae, there's actually a special, like at some point you have to compute the determinant of a matrix. And if that determinant is 0, then this tells you whether or not A1 is the product of elliptic curves. And if it is a product of elliptic curves, then we can terminate because A0 is 2-2 split. And if not, you take another step in the graph. And you repeat this until you find an abelian surface in this special set. So the question, or the way that we can improve our detection, is taking steps in our 2-2 isogeny graph. Can we detect whether the current node that we're on is NN split, where now N is bigger than 2. So we want to detect splittings for N being greater than 2. And if we can do this, then if we can do it efficiently, then this can be used as our improved detection. So a first try would just be to compute all NN isogenies from your node, but this is not efficient at all. Computing an NN isogeny involves taking nth roots, and so it just wouldn't be efficient to do this for large N. So how can we make it efficient? So we set our current node A to just be the Jacobian of a curve C, and let these be its invariants, given by the Isogeny-Club invariance of C. And sort of the magic that Kumar gives us is this map phi of N, which exactly determines whether or not your Jacobian is split. So our Jacobian is split over FP bar if and only if our curve C lies in the image of this map. And by the curve C, I mean the Isogeny-Club invariance. So if you can find an R and S that evaluate to your Isogeny-Club invariance of C, that send this map to your Isogeny-Club invariance of C, then your Jacobian will be NN split. And the bar over the image of phi of N is a super technical condition, which doesn't really matter. But to be precise, you actually have to take the Zariski closure of your image. But feel free to ignore that because it's not that important. But yes, so again, pictorially, because I think it always helps to visualize what's going on. So you have this plane, which is given by these R and S. And your map is just some map in these R and S that maps you down to this weighted projective space. And recall that this is where the invariants of your genus 2 curve lie. So, so Kumar gives you this map phi of N explicitly in polynomials in R and S for N less than or equal to 11. And the image of this map phi of N is sort of a subset or subvariety of this projective space. And if your curve is split, then it will lie inside of this nice purple blob. And if it's not split, then your curve will lie outside of this. So what we want to do is, given a curve C, we want to determine whether or not there are some R and S that evaluate to give you your curve C under the map phi of N. And once we have this R of S, Kumar also gives us the map that takes your R and S to the elliptic curves. So from this, we can get our elliptic curves here. And then as a post-computation, we can just compute all the NN isogenies from our Jacobian and recover the isogeny here. And because now we are guaranteed that our Jacobian is NN split for N less than or equal to 11, this post-computation is sort of efficient. So it really all boils down to determining whether there is an R and S that maps down to our curve C under the map. Yeah, so how do we do this? Well, because projective space is sometimes annoying, we normalize all of our invariants to give us these alpha 1, alpha 2, alpha 3. And we do the same with Kumar's map to give us I1, I2, I3, using the same normalization as we did for these invariants. So now these don't lie in projective space. This is sort of an affine map, and we can get about these projective constants. So yeah, so determining whether or not C lies in the image of the map just comes down to finding a simultaneous solution of this set of equations. So all this is saying is there some R0 and S0 that you can evaluate the maps on to give you your invariants. And if such a solution exists, then your Jacobian is NN split. And if not, if no solution exists, then it is not NN split. You also, because these are rational functions, you have to be careful that the R0 and S0 don't actually make your denominators vanish. But again, it's just a technical condition that you kind of have to check. So how can we how can we determine whether or not such a solution exists? Well, we can turn to elimination theory. And you can try Grosvenor bases, but these aren't very efficient, it turns out. So we use resultants. So we actually compute the resultants of the numerators of these functions. So the resultant of F1 and F2, and the resultant of the numerators of F2 and F3. And we do this with respect to R. And so we eliminate the variable R and we get some polynomials in S. And then once we have these polynomials in S, we just compute their GCD. And if the degree is 0, then our Jacobian is not NN split. And otherwise it is NN split. And the root of this JCD will be your S0. And then you can solve for R0 by inputting it back into one of these equations and taking a root. In fact, in the paper, we actually use a more efficient method. So we generically compute these resultants. So if you view these alphas as variables rather than like being evaluated at a specific curve, then you can pre-compute your resultants. And then at each step, our first step here would just be to evaluate our pre-computed resultants for a specific curve C, and then computing the GCD. And it turns out that because resultants is not very efficient, well, it is efficient, but just not as efficient as evaluating your pre-computed resultants at a specific curve. Okay, so how can we choose the detection set? Well, now our detection set will be a subset of 2 to 11, because Kumar only gives us the map up to 11. And we want it to minimize the same ratio, where in this case, it's the cost of computing our Richelieu isogeny from a given node. And at each step, we only reveal one node because we only compute one Richelieu isogeny. And this doesn't reveal any extra nodes for free. Okay. So now the last slide onto the results. So we implemented and optimized the walks in the 2 isogeny graph and the 2-2 isogeny graph. And we did this with and without this special detection. And we ran these for different primes until we reached a certain number of FP multiplications. And we counted how many nodes were revealed and how many FP multiplications you need to reveal a node. And these were the results. Okay. So I'll just highlight some trends. So firstly, these columns, the fourth and fifth columns correspond to walks without the detection. So if you're just walking in the graph until you reach the subgraph, which in the dimension 1 case corresponds to the Dale-Galbraith algorithm, and in dimension 2 it's the Costello-Smith algorithm. And then the fifth column onwards correspond to walks where we do this additional detection. I've also put in the detection set. So for which n do we actually do this special detection? And the last column gives you the improvement that we get from the original attack. So the first thing to maybe notice is that the improvement in genus 1 compared to genus 2. So genus 2 actually gets a much bigger improvement. So for primes of bit size 100, we get a 25 times improvement in genus 2 compared to only a 5 times improvement. And then if you go all the way up to the bit size being 800, we get an improvement of 120 times in genus 2. And in genus 1, you only get, well, not only, but you get like 18 times improvement. And the reason for this is because if you remember, the number of outgoing nodes in the NN isogeny graph is order of n cubed. So at each step, you are actually revealing a very large amount of nodes. And our detection really boils down to the evaluation of some functions and computing GCDs. So it's not very expensive. Whereas in the genus 1 case, you're only revealing around order of n nodes. And so sort of the comparative gain in genus 2 is a lot bigger. And the second trend that I wanted to highlight is that the improvement as P gets larger gets bigger. So this is both the case in genus 1 and genus 2, where as the prime increases, or as the prime gets bigger, our improvement factor also increases. And this is because taking walks in the graph depends on the prime P, because you're computing some roots. Whereas doing this detection is independent of your prime, because it just depends on the degrees of your modular polynomial, or in the genus 2 case of Kumar's map. And this is the same for all primes. And so the cost of our detection stays the same as the prime gets big, but the walks get more expensive. So you add more of these n into your detection set as your prime gets bigger, and so the relative gain also becomes bigger. So you can imagine as P goes to infinity, you would just stay where you are and just do detection rather than walking in your graph. Okay, so here are just some links. And yeah, any questions? I'm happy to answer any questions.
Thank you for the talk.
Sorry, I couldn't see the chat at all. So if someone had a question, I probably missed it.
Yeah. Thanks for the talk, Maria. Maybe I can go first. I got a bit curious if you tried to figure out how large P has to be before you kind of wish Kumar had calculated more of these polynomials. Because it
Yeah,
seems
so
11 would
yeah,
be.
so that's actually quite interesting, because initially we thought that the bottleneck of our attack would be Kumar's Kumar not computing enough maps. Because modular polynomials, you have them like up to like 100 or like way more than that, but like up to 1,000 even. But Kumar only gives us up to 11. But we ran it, like in our paper, we'll give some even up to log p being 1,000. And 4 and 6 are just the ones, like they're just used for all primes up to bit size 1,000. So we haven't actually, I guess, tried to push it and see how far it would take to even get like 10 into the set. But yeah, I think the problem is that, so when n is 10 and 11, the pre-computed resultants are actually too large. Like the memory required for these resultants is too big. So we have to resort to the method of just doing resultants at each step. And that turns out to not be very efficient. So maybe like future work is just seeing if you can make that resultant thing more efficient to get n equals 10 and 11 to be worth putting in your set. But no, we haven't actually found a prime for which Kumar becomes the bottleneck. Like it seems that 4 and 6 give you enough improvement already, and that adding another n in doesn't make that much difference.
Yeah, oh, that is pretty interesting. Huh?
Yeah.
Can I ask like a follow-up thing, like why it's only for p 100 bits that you use n equals 2 and 3? Maybe we talked about this before. I can't remember, but you sort of seem to skip 2 and 3 at some point. Or I mean, like you only use n equals 2 and 3 in the detection set for log p is 100, but then from 250 and onwards, you only use 4 and 6.
Yeah, so the thing is, so taking a step in the graph for p being bit size 100 isn't that expensive. And so it's actually better for you to take a step rather than doing the detection for 4, for example, because doing the detection for 4, though it reveals a lot more nodes, it's still like you don't include it in the set. But when your prime gets bigger, taking a step gets more expensive. So doing this detection actually becomes more worth it. So this is sort of like the balance you have to find for each prime. You need to find the set for which the n is kind of worth doing the detection. And for primes being small, the detection set is smaller because taking a step is cheap in comparison.
Yeah, that makes sense. But I wonder, could you do like 2, 3, 4, and 6? Or does the...
Yeah, so so we actually in this paper, the detection is, or counting the nodes that is revealed is actually like slightly more complicated because like 3 is a factor of 6. And so you actually, if you do detection for 6, you are doing detection because you walk in the 2 isogeny graph, you're doing the detection for 3 as well. Yeah, so if you do your detection for 3 and then you take it a step in the 2 isogeny graph, that's the same as doing the detection for 6 on that node. And so you actually don't want to include both 3 and 6 in your set because you're like double counting nodes.
Yeah, okay, that makes sense.
So like the detection for 3 is kind of enclosed in the detection for 6. Sort of like yeah, it's you will just detect the same nodes if you do both of them. So
Okay.
you don't get as much gain as you thought you would.
No, yeah, that makes sense.
Yeah.
Yeah, thank you.
But yeah, in the genus 1 case, that's why we actually only do the detection for odd primes to get rid of this like issue with walking in the 2 isogeny graph and doing the detection for like odd for even numbers, because you're kind of double counting nodes if you do that.
Yes, right. Of course.
I can't hear you very well.
Yes. Is it source audible now? Let me wait. Does this change anything?
Yes.
Is there an intuitive sense for why you would have 6 bad extensions and 8 good ones?
Well, there are actually only 5 bad ones, and 1 is the jewel. Oh no. 1 is the jewel, 6 are bad, and 8 are good. Yes. I don't think so. I mean, the most intuition I can give, though this is not a good intuition, is like just thinking about how the kernels can intersect. I think in the hash function paper by Castrick, DeCreux, and Smith, they, I think they actually, like, it's very well written, and I think the way they determine which extensions are good and bad gives kind of an intuition for it, because in the specific case of these two isogenies, your kernels are determined by sort of the order, so your equation for your genus 2 curve is just given by like y squared equals a polynomial of degree 6. So this has 6 roots, and you get like 3 pairs of these roots. And the way that you choose which pairs you have determines your kernel. And so if you think of like the intersection as being like which of these pairs like coincide, maybe that's a better way of like thinking about why there are 6 bad ones, is like how many of the permutations of the roots will have a pair in common.
I think that makes sense.
Yeah, I think it's really well written in their paper, so maybe that's a good reference.
Cool, thanks.
All right.
If anybody else has any questions.
As I mentioned earlier, if you come up with a brilliant question, unfortunately after we've closed the meeting, then you can always ask on this Ask Crypto thread. But yeah, if not, I think we can say thank you to Maria again and stop the recording.